For this problem, the box is not moving, but it's being held up against the ceiling by a force. And it's got a rope attached to it with a tension on it. So let's start with the free body diagram. Alright, so here's the dot representing the box itself. I've got a force going up. This is the force being applied to it. So this is actually the 350 newtons. I'll call that F. And I'll just make a little note over here. That's 350 newtons. It's got a rope pulling it to the right. And remember, with a rope, you cannot push, you can only pull. So I've got a force of a rope over here. And that's going to be the tension in the rope. And because the box isn't moving, in this case, the tension is going to be 250 newtons. It's going to be the force that's pulled down on the other side. And then opposing motion, I'm going to have friction. Friction is going to the left, parallel to the surface and opposing the motion. I'll use a cursive F to represent friction. And then I've got two forces going down. The first one's kind of obvious. That's going to be mg. So here's mg, the mass of the box times gravity. So let's see, that's going to be the mg, or 5 kilograms times 9.8. And the second force is the normal force of the ceiling. See, the box wants to be pushed up through the ceiling, but the ceiling is exerting a force downwards, and that force is going to be the normal force itself. All right, next step, let's sum up the forces. So I'm going to sum up the forces in the x and y directions, sum up the forces in the x direction. I said it wasn't moving in the x direction, so that's going to be equal to 0. And that'll be equal to tension minus friction in this case. So out of that, I get that tension is equal to friction. Now I'll sum up the forces in the y direction. And in the y direction, it's not changing speed, so that's equal to 0. And I'm going to say all the forces going up, which is the force that she's applying at 350 newtons, minus the forces going down. So using only variables, I'm going to write F is going up minus mg going down minus the normal force. So only variables on that one. And that means that, let's see, when I'm looking at this, I have a coefficient of friction, or I'm looking for the coefficient of friction. So if I'm looking for the coefficient of friction, what that means is that I need my definition of friction. So friction is equal to mu times eta. So that's what I'm going to use. What I'm going to do is I'm going to take that mu times eta and I'm going to put it in for friction up here. So when I make that substitution, I know that, let's see, I've got this equation here that I'm actually going to use. T is equal to friction. So therefore, T is equal to friction. So T is equal to mu times eta. Great, but I don't have eta. But I did write an equation for eta right here. So if I rearrange that, I'll write that down here at the bottom. I know that eta is equal to the force applied minus mg. So all I did was move eta on the other side. So up here where it says eta, I know that tension is equal to mu times the force applied minus mg. So let's see, now define mu. I can isolate mu. So mu is equal to the tension divided by, and I'll treat the parentheses like it's one number, divided by F minus mg. So now mu is equal to the tension, which is 250 newtons, because it's not changing speed, so that's equal to the pull force, divided by the applied force upwards, that's the 350 newtons, minus 5 kilograms, divided by 9.80 meters per second squared. And when I do that, I get that the coefficient of friction is equal to 0.831. And since it's a coefficient of friction, there's no units on it.